In the previous lecture, we have discussed about the objectives of the course. That is the first thing. Then we discussed about the outcome, the basic outcomes of the course. That is what a student would learn at the end of the course. And then we have discussed about the basics of what is a structure, what are the internal forces in a structure, what are the basic assumptions in structural analysis, and what is structural analysis. These are the basic things covered in the previous lecture. Now, from here onwards, we proceed further to see what is the purpose of analysis of a structure, first of all. And then we will discuss about what is static determinacy and what is static indeterminacy of a structure. And then we will see the methods of analysis of a structure. Well, the purpose of analysis is to find out the internal forces in a structure. We know that from the previous knowledge, a truss structure which is used as a roof structure, the elements of a truss structure, they undergo axial forces along the longitudinal centroidal axis of such members. They can be tensile force or compressive force. In case of a beam-like structure, where we have transverse loads, the beam undergoes bending. That is why we call that as a beam. And the internal forces in a beam are bending moment, the moment which causes bending due to this transverse loads, and shear force. Shear force is a force which is trying to shear or break the beam. So essentially, for design of these structures, which big structures consisting of truss elements or beam elements, we are required to find out the axial forces, the bending moments, and the shear forces. And design is based on these internal forces. If a structure is statically determinate, that is, if you can find out all the forces, internal forces as well as external forces, with the help of the equations of equilibrium alone. Whenever we say equations of equilibrium, we mention the force equations of equilibrium. For example, if you idealize a structure, say like this, we know that this is a cantilever structure. This is the support of the cantilever, and we can have loads over here. We have a point load, say n point load in the cantilever. To find out the bending moment, shear force in this structure, we can resort to the help of equations of statics alone. The equations of statics or equations of equilibrium are essentially force equations, which you can call as, say, sigma fx is equal to 0, sigma fy is equal to 0, and sigma m is equal to 0. They are essentially algebraic sum of the force components along x direction, say a horizontal x direction. Let this be the x-axis, let this be the y-axis. So algebraic sum of the force components along the x direction is equal to 0. Algebraic sum of the force components along the y direction is equal to 0. And algebraic sum of the moment components or moments of the force components with respect to any point in the plane is equal to 0. That is essentially the equations of equilibrium. With the help of this, you can find out the reactions, the shear forces, and the bending moments. Right. So, if a structure is statically determinate, you can analyze a structure with the help of equations of equilibrium alone. But all structures are not designed as statically determinate. There are structures which are called as statically indeterminate, wherein we require equations in excess of these equations of equilibrium to analyze them. Now we are going to see what is static determinacy and indeterminacy in structures. Well, if you look at this structure, this is a truss structure, a plain truss structure which can be like a bridge truss. There are two supports in this structure. You can see one is a roller support and second one is a hinge support. This carries certain number of members. this portion between these two joints can be called as a member. This portion is another member, and so on. These are joints in the truss. We assume for analysis that all the joints in this truss are pin connected, single pin connected, so that each joint will not take up any moment but will take up only forces. And each joint can translate along the horizontal and vertical, say along two mutually perpendicular directions. And each member will take up only axial forces, will not take up any bending moment or shear force in this case. Now, this structure supported by two supports. As I told you, one is a roller and the other is a hinge. The purpose of providing a roller support is to prevent the movement of the structure supported along a direction perpendicular to the rollers. Say in this case, the motion of this structure along this direction is prevented. So we say that a reaction component or a constraint is imposed along that direction. Whereas a hinge, this prevents the movement of this point of the structure along two mutually perpendicular directions. So movement along this direction as well as this direction are prevented by the hinge. It is as good as holding your pen, say this pen, with these two fingers in your hand, like that. You can see that this structure can only rotate. This pen can rotate with respect to the fingers, but this point of this pen cannot translate along any direction. So these are the two constraints imposed by the hinge support, and this is the only one constraint imposed by the roller support. The roller is like holding your pen, just placing your pen, say on your finger like that. This finger supports the roller, and this finger supports this pen, and this pen cannot move down. But this pen can translate along this direction, along the horizontal direction, perpendicular to the plane of the rollers. So along this direction, the movement is prevented. Now, there are three constraints in the structure, and we have, as given over here, three equations of equilibrium. So we can find out these three forces because of externally applied forces. Externally applied forces are generally acting at the joints only, like this, or say like that, horizontal as well as vertical or inclined. Fine. So these are the constraints or the reactions at the supports. We can find out these reactions with the help of these three equations of statics alone. There are three reactions and three equations. The structure is statically determinate, we say like that. And now to find out the internal forces in these members, we can resort to a method which is known as method of joints, wherein we draw the equilibrium or rather the free body diagram of each joint. Say we take this portion, draw it separately over here, like that, assuming the force in these two pieces or these two pieces of the members as tensile to start with. Arrow marks pointing away from joint represents tensile forces. Let this be force in this member, tensile force in that member, say F1. This is force in the other member which is cut, and the reaction over there which is found out by equations of statics is placed at this junction. Now we are getting a system of forces which are coplanar as well as concurrent. We can make use of the equations of equilibrium. Sigma Fx is equal to 0 as well as sigma Fy is equal to 0, which are the independent equations of equilibrium in case of coplanar concurrent force system, to solve for the forces F1 and F2. Likewise, we can proceed to the next joint, this joint successively, so that there are not more than two unknowns in a joint, and by applying the equations of equilibrium we can solve for all these forces in all these members. So essentially, with the help of the equations of statics alone, these equations alone, we can analyze the whole structure. So that is essentially what is meant by a statically determinate structure. So this is a statically determinate truss. Now, we can see here two typical simple beams. We call this beam as a simply supported beams which is supported by a hinge and a roller. There are transverse loads, maybe point loads like that, there can be distributed loads like that over here. So the support reactions, as in this case, will be 3 in number, maximum 3 in number. There we can expect 2 independent reactions, and here we can expect 1 independent reaction. So because of the external loads, we can find out the reactions with the help of the equations of statics alone. So this beam is also statically determinate. This is the cantilever drawn earlier already on the board. Well, the support over here is called as a fixed support, and we know what is a fixed support. It is as good as holding, say, this pen like this in your palm. You can see that the pen will not translate along horizontal or vertical, will not rotate with respect to a perpendicular axis about the support. So we say that this pen is fixed, or this structure is fixed at this support. So all the 3 possibilities of movement in a plane, that is a horizontal movement, a vertical movement, these are the independent translations in a plane, and a rotation with respect to a perpendicular axis. These 3 translations are prevented by means of a vertical force, a horizontal force, and a couple or a moment. So 3 reactions or 3 constraints are provided by a fixed support like that. And if you have external forces, say like point forces or distributed forces, you can find the reactions by applying the equations of equilibrium alone. So we call these 2 beams also as statically determinate. The equations are called as equations of equilibrium or equations of statics in a plane. So that is brief about what is determinate structure. But as I told you, a structure is not going to be designed as a statically determinate one alone. For example, if you, these are briefing regarding what is determinacy and what is indeterminacy. Before going into that, let us see here a typical structure. Well, let us start with the cantilever itself. This cantilever, suppose we have a roller at this free end of the cantilever. The number of reactions in this case suddenly increased by 1. We have already a vertical reaction, a horizontal reaction, and a moment at this end due to fixed support, and now we have introduced a vertical reaction due to the roller support over there. So because of these external forces, let them be point forces or distributed forces, we are going to have 4 reactions now. Now we have only 3 equations of equilibrium as already discussed, which are sigma fx, sigma fy, that is along 2 mutually perpendicular directions, force components along 2 mutually perpendicular directions are equal to 0, as well as sigma m is equal to 0. About any point in the plane is equal to 0. Right. These 3 are insufficient to solve for 4 unknowns. That is pretty clear. So we have to resort to some other conditions. So we say if a structure is indeterminate because of equations of equilibrium alone, we call that structure as statically indeterminate. Now we are going to see how to treat the statically indeterminate structures and which are the methods of analysis for them. So before that, let us go through a few points regarding determinacy and indeterminate structures like this. It is given here as a structure is determinate statically if it could be analyzed completely with the equations of statics alone. It is described in the previous section already. And now static indeterminacy of a structure is hence defined as the difference between the number of unknown forces, that is internal and external, and the equations of equilibrium available from statics. What is meant by the number of unknowns in say internal and external would be clear with the previous with the next discussion. Sorry. We proceed further. For a pin jointed plane frame, that is a structure may be like this. With 2 supports, so 2 hinges like that, there are loads acting at the joints like this. The supports, let us call them by name, say A and B. The support reactions are, here you can expect a vertical reaction and horizontal one. Here also we can expect a vertical and horizontal reactions. Let us say like that. Now the number of unknowns in this case is equal to, let us say number of unknowns, say reactions is equal to 4 and number of equations available is equal to 3 from statics. So the difference between the number of unknowns and the number of equations is equal to 1 here. We say that is the degree of static indeterminacy. There can be cases where more members are introduced in the structure, say like this. And please remember, these line segments represent the centroidal longitudinal axis of the members only. They are not the actual members. So this is a member. This also is a diagonal member. Another 2 diagonal members are there on top. Now, if you count the number of internal as well as external forces, remember R represents only the external reactions. If you count the internal and external forces, the internal forces are provided by the axial forces in members. So suppose if you have m number of members in this, number m in this case would be equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 members and 11 number of axial internal forces can be tensile or compressive in this structure. So internal forces plus external forces will now become m plus r is equal to 11 plus 4 is equal to 15. And as we have discussed, to analyze the structure, we have method of joints. We write the free body, we draw the free body diagram of a joint and write the equations of equilibrium applicable to that joint. Likewise, if there are j number of joints, j is equal to 1, 2, 3, 4, 5, 6 for the structure. Each joint can supply 2 equations of equilibrium. So if we have j number of joints, there are 2j number of equations. Equations is equal to 2j. In this case, it is equal to 2 into 6 equal to 12. So the degree of static indeterminacy defined as d suffix s is equal to, for this structure, it is equal to number of unknowns, internal and external, minus number of equations, which is 2j. That is equal to 15 minus 12 is equal to 3. And you can identify, say, one of the reactions here. This can be this reaction is an unknown. We can choose that there is an unknown, and you can also choose, say, the force in this member and the force in this member, say, as unknowns. If you remove this member and also this reaction, that is, if you make this support as a rotor support, the structure will become statically determinate. That is clear. If you remove this diagonal member and make this support as a roller, the structure will become statically determinate. We are going to get this number equal to 0 in that case. So if you consider these 3 as, say, unknown forces, or we call them as redundant forces. Redundant. We can say that the number of redundant forces is equal to the degree of static indeterminacy in this case. Now let us proceed further with the slides. What is given here is, for a pin jointed plane frame, whatever we have discussed already is given here in a statement. If J, M, R represent number of joints, number of members and number of independent external reactions respectively, then the number of unknown forces is M plus R and the number of equations of equilibrium is 2J. Hence, degree of static indeterminacy is ds is equal to M plus R minus 2J. That is very clear from this example. If you proceed further, for a pin jointed space frame, Suppose this is a, you can extend that to a space frame, so that each joint can translate, each free joint can translate along the three mutually perpendicular directions, along say horizontal, along vertical, and along a perpendicular direction. Let us call them as x, y, and z directions. In such a case, as given here, the number of equations of equilibrium would be 3 times j. That is, in addition to the sigma fx equals 0 and sigma fy equals 0, we are going to have a sigma fz equal to 0 as the third equation of equilibrium for a concurrent force system in space. These three are going to be the equations available over there. So if we have j number of joints, 3j number of equations would be available like that, and the degree of static indeterminacy in that case would be number of unknowns, internal plus external minus number of equations, right? Example, a truss like that, you can count the number of members equal to 50, number of joints is equal to 8, there are 3 hinges supporting this truss, so R is equal to 2 into 3, 6. Further, degree of static indeterminacy of the truss in this figure is equal to ds is equal to m plus r minus 2j, that is 15 plus 6 minus 2 is equal to 5. And you can identify as a choice of redundance this one. The force in this member, and the reaction, say horizontal here, and the reactions horizontal and vertical here. So these are the 5 possible redundant forces. You can have other choices too. It is only for illustration. That is, if you remove this support from here and make this support as a roller, and if you remove these 2 members from this truss, the truss will become statically determinate full. Further, in case of a rigid jointed structure, say a beam, if you just make a cut in a beam like that, so that is a continuous beam. It was continuous initially like this. The beam is given 2 supports, one is the roller, other is a hinge at this end, and with a vertical plane I make a cut over here. I break that into 2 pieces. There are external forces, of course, in the beam, transverse forces, point loads and UDL. If I break that beam, somewhere in between the 2 supports, I am going to get the internal forces exposed, and they are P, axial force acting along the longitudinal centroidal axis of the beam, a shear force F acting transverse to the beam cross section like that, and a bending moment, say M, which is along this direction, perpendicular direction in the beam. So this moment is supposed to bend the beam at that cross section. This force F, shear force, is trying to shear or break the beam at that cross section. This is the axial force, which may be axially compressive or tensile, right? So here also the same notations are used for the same kind of forces and moments, and you can see that when you bring them together as a single piece again, the forces P and P neutralize, F and F will be in equilibrium, and M and M will be in equilibrium. That is how it is done. So if you break a beam member like that, you are going to get 3 internal forces. Likewise, if you have M number of members in a frame or a structure which consists of such members, such beams, 3M will be the internal forces. 3 for 1 member like that, and M is the number of members, so 3M will be the number of internal forces in such a member, and R is the number of external reactions, as we discussed before. It is given. R is the number of independent constraints. Each joint in a beam, each joint like that in a beam can provide 3 equations of equilibrium. They are, there is no sigma fz. This is regarding a plane frame, rigid frame. So the equations of equilibrium are sigma fx equals 0. There is the first one. Sigma Fy equals 0 and sigma M is equal to 0. These three are the equations of equilibrium for a joint. In this case, if that is the case, the degree of static indeterminacy is equal to 3m plus r minus 3j. Illustration can be obtained from this. This is known as a continuous beam. A beam continuous over several supports. A is a fixed support. B, C, D and E are roller supports. You can consider AB as an element in the beam, BC as the next span or element in the beam. Likewise, we have 1, 2, 3, 4 number of elements, and this portion is considered as an overhang. The effect of this overhang is considered as a moment and a force over here. We will discuss that later in detail. So for the time being, we have this continuous beam consisting of 1, 2, 3 and 4 number of elements. That is, number of members is equal to 4 over there. Yeah, M is equal to 4 here. Number of joints, A, B, C, D, E are the joints. That is equal to 5. Number of reactions due to external supports, 3 plus 1 plus 1 plus 1 plus 1 becomes 7. So ds is equal to, using this as a relation, it would be 3 into 4 plus 7 minus 3 into 5 is equal to 4. You can identify these 4 number of forces, say, as the reaction here, the reaction here, the reaction here and the reaction there. That is one choice. So if you remove, say, these 4 reactions, this structure will become statically determinate. Or else, you can also consider, so the moment here, the moment at this support, the moment at this support and the moment at support D. If these 4 are considered as the unknown forces or redundant forces, then also we can make the structure statically determinate. So this structure is statically indeterminate to degree 4.